Connor Fleeser. I'm the technical lead for the Infant Incubator project on the Innovative Global Solutions Enterprise. We set out to develop a low-cost, low-power infant incubator solution in order to address high mortality rates in Sub-Saharan Africa. Our capstoning students will now walk you through the work that they performed over the last year.
The housing team's main goal is to develop the physical structure of the infant incubator. This year, we fully designed a new prototype and are now in the final stages of assembly. Our incubator features a durable HDPE frame and clear polycarbonate windows. We've added wire management by adding holes in the frame to discreetly run the wires to the PCB board in the bottom of the incubator, as well as adding in a secluded heating compartment to better maintain humidity. We've also collaborated with other sub-teams throughout the year to ensure every component fits. Plus, it's an IKEA-style build, so it's easy to assemble and ready to go. The controls team is responsible for designing and building the incubator's user interface and temperature control system. The interface includes an LCD screen, 5 buttons, and a dial. It displays the infant's vitals along with the incubator's temperature and humidity, which are monitored by sensors communicating via I2C. The temperature sensor regulates the fan and heater to keep the temperature within 1 degree Celsius of the user's setting. If the infant's vitals or the incubator's environment go out of range, an alarm system triggers, activating an LED and a buzzer to alert medical staff. The entire system is coded in C++ using Arduino IDE and powered by a Teensy 4.1 microcontroller.
After completing the circuitry on a breadboard, it was then converted into a schematic in Eagle, as shown on the left. The schematic was then transferred onto a board and routed. The following 2-layer board with overall dimensions of 80 by 100 millimeters will be ordered from JLC PCB. This is a 3D model of the final PCB, which includes the MOSFETs, resistors, and capacitors placed on the PCB. Next steps for the controls team will include soldering on the Teensy, light, buzzer, and buttons, as well as all of the exterior components.
Our environmental system is designed to maintain optimal conditions for neonatal care by regulating both humidity and temperature levels. It automatically adjusts as needed, reducing risks such as dehydration, respiratory issues, and thermal stress. This year, we have made many exciting changes to our design. In previous iterations, we incorporated an off-the-shelf humidifier, whereas this semester, we built our own completely from scratch. In addition, we also designed a PLA 3D printed humidifier casing. This casing is easily refillable as well as vapor smoothed to remove layer lines for easier cleaning.
The Vital Sub-Team oversees the sensors that directly monitor the infant's health, including body temperature and heart rate.
Since last year, we have calibrated and integrated a new temperature sensor and revised the casing that contacts the infant. Inspired by other monitoring systems on the market, the design involves a detachable sock that contains both sensors as well as hook and loop tape for an adjustable fit. The sensors are in series to prevent excess wires in the incubator with the infant.
Our team would also like to give a special thanks to our sponsor, Plexus Corp., especially Nathan Tetzlaff and Lindsay Hooker, as well as our advisor, Dr. Manser. Thank you all for your support.